So we had seen a few concepts on CMRR, right? Which is common mode rejection ratio. And we got to know that common mode rejection ratio is a very important concept, okay, because we are bringing both the base voltages together, we are shorting them together and giving a constant voltage across them. Now, ideally, if this is going to be the same, then it means that we should not have any differences. So which means the output should be about 0, but then in practical, we will find certain offsets, right? So common mode rejection ratio plays a very important role and in making the circuit more reliable and constant. So we can know that if this circuit has CMRR of this value or PSRR of this value, then how reliable this circuit is going to be. Remember, the tabulation which I had just put up. Yes. So this will help us understand, what is the capacity of my circuit? What is going to be the CMRR? Okay. Now, keep in mind that these are taken for about 10 kilo ohms. Okay. For about 10 kilo ohms. Okay. Fine. And you can see that the minimum value is about 70. And typically it reaches to about 90 as well. Okay. So these values are to be kept in mind. So if I can see a better value here, it means the tolerance is high. Okay, it's just like, the noise tolerance. Even though there is noise signals that is coming through, your circuit is able to withstand the noise, but still pass on the communication signal. Okay, so basically communication, we have in communication, we can also associate noise signals, right? Noise signals are associated by default, even though we do not want them to be associated. So if it can withstand a large amount of noise, okay, if it can look into all these parameters, then I can say that my circuit is really good. My package is really good. Okay, so based on this, we had discussed on CMRR, right? And then we saw a small circuit, and we also looked into the common mode gain, right? And ultimately we got to know that CMRR is a multiple of 20 and the logarithmic value for open loop gain, common mode gain. Okay, right? So this one should be kept in mind. So today we will look into this example. Okay, so I hope all of you have your calculators ready with you, right? You have your pen and your books ready with you, right? So that we can just get started with the problem. So we are given with a problem stating that a 741 op-amp is used in the circuit. Okay, so I have put up the circuit here. Calculate the typical output voltage that would result from a 100 millivolt common mode input. So you should get an idea that we are talking about CMRR here, okay, because it is referring to what? Common mode input. So that is one clue that you can take. Yes or no? Right? This is
Yes.
one clue that you can take from the question. And what else is the question asking us about? Calculate the output voltage that would result from 100 millivolts. So which means this 100 millivolt is going to be my input. Okay, so that's going to be my input. This 100 millivolt is going to be my input. Okay, so we need to calculate the output voltage. So V naught output voltage we should calculate. Fine. So now we know that our ACL, okay, closed loop gain, we have resistors R2 and R3. So this R2 and R3 is acting as what? We have seen this previously. It is in what mode? R2 and R3 Only this section. In what mode is it? We have seen this circuit, right? This is not new circuit. Yes, can I have some response? R2 and R3 here in this circuit is in which mode? Don't you think it is, we were using this voltage divider, right? The voltage divider format, correct?
Yeah.
Students, one thing, whatever concept that you are learning, you should not forget. Okay, just make sure that you make a note of it. Okay, some things are very much important where you make note of it. Your personal notes are going to help you at the end of the day. Okay, of course I will be sharing in my materials, but then whatever personally that you make note, okay, you will be learning it a lot, and that is going to help you during the time of examinations. Okay, fine. So this is acting like a voltage divider. Okay, and so we are going to use the formula R2 plus R3 divided by R3. So this is going to be my gain for closed loop mode. So you can see that it is a closed loop here, right? It's a closed loop. And what kind of feedback is it? Is it a positive feedback or a negative feedback? Look at the circuit and tell me.
So positive.
You're sure it's a positive feedback? It's a negative feedback, right?
Yes, sir.
So because part of the output, see, ultimately what is feedback? Part of the output fed as input. Okay. Now, is anything connected from the output side here in the positive terminal? Nothing, right? There's nothing. There's nothing that is connecting to the output terminal. But then there is something that is getting connected from here, isn't it? Right? So this becomes my negative feedback. Okay, this becomes my negative feedback. Now I have told you the importance of negative feedback. What is it? What is the importance of negative feedback? Basically, there are two types, right? Positive feedback and negative feedback. So what is the importance of negative feedback? Yes.
It makes sure that we don't get a very high amplification.
Very good. So ultimately, we are trying to reduce oscillations, right? So very high amplification, in turn, if I give positive feedback, then it's going to increase the number of oscillations. So increasing the oscillations are nothing but high frequencies, isn't it? So when I give a negative feedback, these oscillations are to an extent reduced. So if these are reduced, then it means I'm trying to bring the system more stable, right? So negative feedback is given to make sure that my system is made more stable. Ultimately, do we need stable systems or unstable systems? What are we interested in? Yeah, what are we interested in? Are we interested in stable or unstable systems?
Stable.
Stable, right? So stable means reliable. Okay, fine. So if you can calculate this, have you verified the value? Are we getting 56.8? Someone please help me out in verifying these values. Are we getting 56.8? Are we?
Yes, sir.
Okay. And why is that there is no any kilo ohms here for 56.8?
So we have kilo in both numerator and denominator.
Correct. So it gets cancelled out, and ultimately we just have a small number. Okay. So this is nothing but 56.8 ohms. Fine. No, not ohms. We are talking about the gain, right? Okay. Now we have the data sheet of 741, which is op-amp. Okay, and we saw that the CMRR is about 90. Now, what is this data sheet that I'm talking about? You know, I have actually put it up here. You can see this arrow mark here. Yes.
Yes, sir.
Yeah. Okay. So using the data sheet, we know that, okay, the CMRR is about 90. Now this becomes a missing data in the question. This is not given, isn't it? So some things, you might have to remember and use it for your problems, right? Or sometimes I would have mentioned in the question paper, stating that, consider missing data. So in that case, you can remember that the CMRR value of op-amp is about 90 dB. So once you take this 90 dB, CMRR is equal to anti-log of 90 dB divided by 20. Can someone tell me why is that we are dividing by 20? Why is it that we are dividing by 20? Is there a specific reason? Can you flip back your pages and look into the formula and tell me
And the
why is
formula
it
is
that?
20 log.
Yes.
That's
So it
right.
is 20 times log. So which means I have to do the reverse, isn't it? So log becomes anti-log into 20 becomes divided by 20. Fine. So I'll be getting the value 31623. Can someone tell me how are we calculating this anti-log value? How do we calculate anti-log value? Log, of course, you have a direct button in your calc, right? You just press it and then it comes up. But anti-log, how do you do?
E power of.
Yeah, you can do that, or 10 raised to the value, which is 90 divided by 20. How much do you get 90 divided by 20?
E power 90 by 20 also get.
Yes.
90.
Correct. Right. So which means we are looking at the value about 31623. So I hope all of us are getting this value. Yes.
Yes, sir.
Please verify. We are getting it right. Okay.
Yes.
Fine. So now, we know that the output, okay, the output voltage. See, ultimately, they've told us to find out what output voltage. So we want output. This is in closed loop mode is equal to input, which is in common mode, format, divided by CMRR into ACL. Now, if you can recall, okay, we had seen this formula. Okay, we had seen this formula. So ultimately, my input, which is in common mode format, which I told you, okay, is going to be this, right? You can see that in the input, you have this 100 millivolt. So this is going to come in my input, and the common mode value, which is 31623. So this comes up here. And 56.8, where are we getting it from? From here. Okay. So are we getting about 180 microvolts? Please verify.
Yes, sir. Rounding off, we get that.
Yes, yes. So ultimately, we are getting about 180 microvolts. So what is that we are understanding from this problem? What is our takeaway? What is our takeaway from this? We learned the formula of ACL, right? So ultimately, first thing that you can do is you write down this formula. Okay, the formula which is here. So once you have that formula handy, okay, okay, so I want you to first note down this formula. So once you have this formula handy, then you will know what terms to actually look into, right? So you will know that, of course, you have the input for common mode format, right? So you don't have to calculate that. You can directly take it from the question. Then you will know that, yes, I need CMRR value. So ultimately, then you will remember that the CMRR value is about 90. Then you divide it by 20, and then you take a 10 raised to that value. Okay, and that's going to give you this. So you have both numerator and denominator. Next, you will know that you need the value of what? ACL. So how will you find out ACL? Closed loop gain. So closed loop means you refer to the circuit. Closed loop. Okay, so this is the only way that I can get a closed loop. So which means, is R2 only responsible for it? No, I have R3 as well. So which means you are going to get the voltage divider formula in. You're going to pitch in that formula. So R2 plus R3 divided by R3. So ultimately you're going to get a value. So my way of looking at this is that, first you have the formula and then try to fill in the bits and pieces. Okay, you can fill in the bits and pieces and find out the final value. Is that clear, students? Any doubts in this problem?
No, sir, no doubts.
Okay, so again, now we shall go back to the question, right? We shall see a 741 op-amp is used in the circuit. Find, calculate the typical value of output voltage. Yes, output in CL mode, closed loop mode. That would result in having an input of 100 millivolts in common mode gain, right? Common mode voltage. So we have satisfied everything. It is a good practice to once again read the question after getting the results to find out if by chance you have missed out anything. Okay, so as much as possible, once you note down, once you see the question, please note down the values, the given data. Okay, given data and what has to be found out. So it will be easy for you to analyze and check as to how you can go about solving the problem. Fine. So have this way of doing things, so it's going to be easy for you. Shall we move on to the next problem?
Yes, sir.
Yeah. Okay. So the next one that I am looking into is yeah. So this is a simple problem here. Okay, power supply rejection ratio. So we are it's a simple problem, and we are going to analyze and we are going to check as to how we are going to solve it. Okay, a 741 op-amp uses plus or minus 15 volts supply. Can someone tell me why is that we are using plus or minus here?
So one for the inverting and one for the non-inverting.
Very good. So one gets into the plus terminal and the other one gets into the minus terminal, right? Okay. So op-amp uses this supply with 2 millivolts and 120 hertz ripple voltage superimposed. Okay, now this is the voltage value, this is the current value, and this is the frequency value. So I have both I have all the three: voltage, current, and frequency values. Calculate the amplitude. Okay, now this is important. We have to calculate the amplitude of the output voltage produced by power supply ripple. So again, this is giving you a clue stating that this is referring to PSRR, okay, power supply. If the circuit has non-inverting closed loop gain of 50, another very important data here, okay, we are having ACL of what? 50. Okay, so we have the values here given. The values, which is 15 volts, okay, 2 millivolt, and let me probably use another one so that it becomes easy for you all. Yeah, okay, so this is the value given, right? And then you have to find out, you have to calculate the amplitude. Okay, so how much of variations that is happening. Okay, so power supply. So ultimately, what is power supply rejection ratio now? We have seen, right? What is PSRR? Yes, what is PSRR? Can someone help me with it?
Asking the formula or
The definition you can tell me.
there is a measure of how effective the amp is in dealing with variations in supply voltage.
Very good, very good. So we are looking at how effective it is able to stabilize, or it is able to compensate the changes that is going to happen in the power supply. Okay, fine. So having this definition in mind, and the values that to be created, that has to be computed, and the values that we have here, we will move on. So just like the previous problem, we know that the PSRR is about 96 dB. Okay, so some of the things, okay, which is very much required, okay, you will have to remember. If not, then probably I will put it up in the question. Okay, consider the PSRR to be about 96, so that should be useful. So again, here we are using the same tactics, right? We are creating, or we are taking up anti-log, and we're dividing by 20, the reverse, right, of the formula. And please check, are we getting about 63096?
Yes, sir.
Yes, we are getting that value. Fine. So having this value, okay, as I told you previously, okay, you should have the formula first written. Okay, the formula first written, then you can start filling in the values into the formula. Okay, fine. So the output, okay, we are writing RIP. It is because ripple. Okay, the ripple format of output voltage. Ripples means there are some disturbances there. Okay, and here VS rip, which means this is my supply voltage. Okay, supply voltage, and this is in ripple format. And PSRR, okay, we are going to get the value of PSRR, and ultimately ACL is anyway given here, which is 50. So here you can see that I'm taking the currents here, which is already mentioned, 2 millivolts. Okay, and then I'm taking the PSRR value here directly. Fine. Right, the PSRR value is directly taken, the closed loop gain is taken, and I'm taking the value of these currents. And please check, are we getting about 16 microvolts? Calculate and tell me if we are getting about 16 microvolts. So see, the other way of solving this is probably you can take 63096 and take it as an inverse, multiply with 2 milli. Okay, and that answer again you can multiply with 50. Yeah. So are we getting that value?
Sir, is it 63.096 or 6390?
1 minute. Just divide this 96 divided by 20 and then 10 raised to the value. How much are we getting? Yeah, it is 63096.
Okay, sir.
Yeah. It is coming like upon 95.73. Okay, so we can round it off as 96. So 63096.
So then the answer I'm getting is 1.58 micro.
Micro, no? So
Same, sir. Even I'm getting that one.
1.58.
just try to
If
put
I
15.
16,
15.
so 15.8 into 10 to the power minus 6.
So that is approximately to
16,
the
sir.
value, right?
Yes, sir.
So we have to take 15, isn't it? How much are you getting? Is it fine?
15.84.
15 points. Yeah, so we will approximate to 16. Okay, into 10 raised to 6. So that gives us micro. Fine. So again, we'll get back to the question. A 741 op-amp uses 15 volt supply, and this is the currents and the frequencies, the ripple voltage, and it's superimposed. Calculate the amplitude of the output voltage, which means, see, don't get confused. When I say amplitude of output voltage is as good as calculating the output voltage itself. Okay, so when I say amplitude, it means it is actually referring to the waveform. When you draw the waveform, okay, this refers to my amplitude. This part refers to my amplitude. Okay, this section refers to my amplitude. So don't get confused. It is as good as finding out the output voltage. Okay. The output voltage produced by the power supply. The circuit has non-inverting closed loop gain. Fine. So we have 50 and we have got our answer. So any doubts here, students?
So getting 1.6 still, I don't know where I'm wrong.
Exactly, sir. 1.59.
Not getting?
It's
15 we are not
1.58
getting.
into 10 power minus 6.
Exactly.
So ultimately, you look at what formula is needed, okay, and how you're going to fill in the values. Okay. So any doubts here in this problem? Is it fine?
No, sir. It's fine.
Yeah. So now moving on to our next. We had discussed till this point, and we just had to see just a small formula which was left out, and we will just look into it. So we were seeing that if in case there is a change, okay, instead of being about 0.7, if it's 0.69, then what is going to happen? There is going to be about minus 10 millivolts. Okay, so this is going to be your offset voltage, input offset voltage change. Okay, fine. So if we have to bring out in the form of formula, okay, so it results in the output always being slightly different from the input voltage. So we have the output. Generally, what is the concept? We want the output values, okay, to be as same as the input values, right? But here, due to this changes in offset, okay, because of these changes here, okay, see, because of these changes here, 0.7, 0.69, okay, you are seeing that there's a difference of about minus 10 millivolt, right? Okay. So when there is a plus 1 volt, for example, the output will be, so how will I calculate? So I'm bringing it in the form of formula. V naught is equal to Vi plus the offset. So 1 volt, for example, and minus 10, what we had previously. So which means my output voltage is going to be about 990 millivolts instead of having 1 volt. See, input side I have 1 volt, but then output side I'm getting about 990 millivolts. So do you think this is acting as an ideal op-amp? Where is plus 1 and where is 990 millivolts? There is a huge. So we are seeing that, you know, there's a huge difference. Okay, so this difference is about, you know, minus 10 millivolts. So when the input is about minus 1, then it becomes the reverse. So instead of being less, you know, it becomes more. So it adds up. It adds up. So the output is going to be minus 1.01 because it becomes minus of minus, right? So it adds up, and we are seeing that the values doesn't remain the same. So you can see that plus 1 volt here, 990 millivolts, these are not remaining the same. And it's true for the reverse as well. Okay, if I take minus 1 volt, instead of having a lesser output, I'm going to have a greater thing, right? When the input is minus 1 volt, the output is going to be how much? Minus 1.01. So we want both the input and the outputs to be the same, but then that's not the case here, right? You can see that's not the case here. It's all different. In a voltage follower, the output offset is equal to input offset voltage. Now, did you understand this concept which I'm trying to bring out here, students? Yes? Have you all understood? Have you all understood
Yes.
as to how we have got this? Yeah. So this is the importance of, you know, maintaining offset voltages. Okay, we are trying to make sure that these changes are nullified. Okay, in a voltage follower, the output offset is equal to input offset voltage. So ultimately, what's an voltage follower? Whatever is at the input side, the same thing should be followed at the output. So hence the name voltage follower. But do you think the purpose is being solved here, or, you know, is it really acting as a voltage follower here? Is it acting like a voltage follower? Yes, no. Students, I need your response. After seeing these differences in input and output, do you think this voltage follower is holds good?
No,
Does it holds good? It doesn't hold good,
Yes, sir.
right? So you have different voltages at the input side, you have different voltages at the output side. So which means, how is it called a voltage follower? So this is practicality. Okay, so practically you cannot find them having the same values. Okay, right. Now, for example, okay, now if I'm using an amplifier, okay, an amplifier with a closed loop gain, we have seen this ACL, right? ACL. The input offset voltage produces an output offset. So output offset is nothing but your input voltages that you are giving, okay, along with the gain, because output is ultimately gain into input. Do you all agree with that?
Yes, sir.
Yeah, right. Now, since we have the gain which comes into picture, okay, so what's happening? What's happening here? The gain is multiplied with the input values. So do you think this difference is going to be marginal, or is it going to be very substantially different because of the term ACL?
It'll be different only, sir.
It will be highly different, you know, because
Yes,
as we all know, these op-amps will actually magnify, you know, with a higher value. It has infinite gain, right? So ACL really plays a major role, and you can find that the output voltages are by far, you know, hugely different from the input. So which means an amplifier, for an amplifier, the output offset voltage will be much larger than the case of a voltage follower. So which means it's not going to act like an ideal op-amp, right? It's not going to act like a voltage follower, but then the differences are going to be really huge. Okay. ACL is, now this is very important. Okay. I want you to please make note of this. Okay. Because it will be asked, okay, in your examinations and in your tests, and you have to keep this point in mind. ACL is referring to non-inverting gain. Very important, non-inverting gain. Even though, okay, even though whatever format that it is in, if the circuit is used in inverting format or non-inverting configuration, but still ACL is always referring to non-inverting gain. Okay. ACL is always referring to non-inverting gain. It is not referring to inverting gain. It's always assuming that this gain is referring to the non-inverting configuration, not the inverting configuration. Is that clear, students?
yes, sir.
Yes. Is it clear? Any doubts here?
No, sir, no doubts.
Fine, fine. So that is why, you know, I planned of solving the problem first and then coming down to ACL, so that you'll know the impact of how this ACL plays a major role. Okay, so with this, you know, we conclude today's class, and we will probably look into few more concepts. Okay, the upcoming concepts we have seen: input and output offset voltages. The next that I'm going to pick up is input bias currents. Okay, wherein we will come up with the electrical properties of the op-amp, and we'll see a small circuit, okay, in the non-inverting configuration, and we'll also solve a problem, after which I'm planning with input offset current. Okay, now that we have seen voltages, right, input and output voltages, so we'll be looking into currents, the input and input offset current and the input bias current. Okay, and then we will see the combined effect of the errors in the input, then probably we'll solve a problem and get into offset nulling. Okay, so this is my plan for my next week, and we'll be looking into a few more concepts with the impedances, slew rate, and frequency limitations. Right, so that's my plan for the upcoming week. Okay, so I'll be posting in the materials, and you can look into it, and if any doubts, feel free to always get back and we can have a discussion. Right?
Yes, sir.
Fine.